All right, let's talk about a choice. It's a choice that every single programmer has to make, and it seems so small, but the consequences can be, well, massive. We're talking about a decision that could be the difference between a problem solved in the blink of an eye or a catastrophic failure that takes 11 days.
And this is it. This is the classic dilemma. Do you go with the code that's simple, straightforward, and easy to write? Or do you put in the extra work for something that's way more complex but ridiculously fast? It feels like an easy choice, but as you're about to see, the wrong answer can be a really, really big deal.
So picture this. Let's imagine a programmer. We'll call him Bob, and he works for NASA. A rocket is coming down for a lunar landing, and it has exactly 10 seconds to figure out the perfect spot to touch down. The pressure is on. Bob has 2 search algorithms ready to go. He just has to pick one.
Now, Bob's a smart guy, so he runs a quick test on a small list of 100 items. The simple search, the one that was easy to code, takes 100 milliseconds. The faster one, binary search, takes just 7. Bob looks at this and thinks, okay, sure, 7 milliseconds is faster, but my simple code is way less likely to have a bug, so he plays it safe. I mean, the difference is practically nothing, right?
And this is the question Bob completely forgot to ask, because the real calculation for landing a rocket doesn't use 100 items. No, it uses a list with 1 billion items. That tiny test he ran, it gave him a completely warped idea of what was about to happen.
Yeah. Had Bob actually run his simple and safe algorithm on the real data, it wouldn't have taken a few extra milliseconds. It would have taken 11 days. The rocket would have been nothing but a crater on the moon. And it all came down to that one, seemingly logical choice.
And that gets to the absolute heart of the matter. The problem wasn't just that one was a little faster than the other. It's that as the list grew from a tiny 100 items to a massive 1 billion, their running times grew at wildly, dramatically different rates. That's the trap that Bob fell into.
So how in the world do we avoid making Bob's mistake? How can we possibly predict this kind of explosive growth without, waiting 11 days for a test to finish? Well, luckily, computer science has a really powerful tool for exactly this. It's called Big O notation.
Now here's the crucial thing to understand. Big O doesn't measure speed in seconds or milliseconds. I mean, that can change depending on what computer you're using. No, instead, what it measures is the growth in the number of operations. It's all about predicting the shape of that performance curve as things get bigger.
So if we look at Bob's problem again through the lens of Big O, his simple search is what we call O of n, or linear time. All that means is for n items in a list, it might take up to n steps to find what you're looking for. But binary search, that's O of log n, or logarithmic time. It's way smarter. It doesn't check every single item. It cuts the problem in half with every single step.
Okay, to make this really click, let's just forget about code for a minute. Let's use a super simple analogy. Imagine you have a piece of paper, and your job is to create a grid with exactly 16 boxes on it. So, algorithm number 1 is our O of n approach, just like simple search. If you want 16 boxes, well, you draw them, one by one. You draw box 1, then box 2, then box 3. It's direct, it's simple, and it takes you exactly 16 steps to get it done. Now check out the O log n approach. Instead of drawing, we're just going to fold the paper. One fold gives you 2 boxes. Fold it a second time, you've got 4. A third time gets you 8. And just one more, a fourth fold, and bam, you have all 16 boxes. We get the exact same result, but in just 4 steps instead of 16. That is the magic of logarithmic growth. And this really drives the whole point home. It's not about how fast your pen is or how powerful your computer is. It's about choosing the right strategy, drawing versus folding. The number of operations is what really truly matters.
Okay, so now that we've got a handle on the difference between ON and O log n, let's zoom out a little, because these are really just 2 points on a much, much wider spectrum of algorithm speeds.
Here are 5 of the most common runtimes, ranked from fastest to slowest. We've already met O log n and ON, but you can see things get a lot worse. ON squared usually means you're checking every item against every other item. And then you get down to the bottom, ON factorial, which is factorial time. And that's where things get, well, appalling is a pretty good word for it. And this table is where the theory just slams into reality. With a tiny input, like 16 items, the differences are fine, they're manageable, but just jump to a little over 1,000 items, and look what happens. O log n barely even budges, going from 4 to 10 operations, but ON squared, it explodes to over 1 million. This is that scaling problem in action.
So if you want to see what that truly appalling end of the spectrum looks like in the real world, we have to talk about one of the most famous problems in all of computer science, the traveling salesperson.
The idea seems simple enough. You've got a salesperson, they have a list of cities to visit, and all they want to do is find the absolute shortest route that hits every city just once and then returns home. I mean, how hard could that possibly be?
Well, the most direct way to solve this is to just calculate every single possible route. For 5 cities, that's 120 possibilities. Okay, a computer can handle that. For 7 cities, it jumps to over 5,000. But for just 10 cities, you're looking at over 3.6 million possible routes. This is that factorial growth, that O(n) factorial, and it is an absolute beast.
And here's the punchline. This problem grows so incredibly fast that once you get to around 100 cities, a computer trying to check every single route would literally be running for longer than the sun is expected to exist. It is, for all practical purposes, unsolvable this way. It's one of the great unsolved problems for a reason. No fast algorithm for it is known to exist.
And this kind of brings us to the final and I think most exciting thought. Big O notation isn't just about avoiding an 11-day coding mistake. It's about understanding the very boundary of what is computationally possible. Problems like the traveling salesperson feel impossible today because of that insane O(n) factorial complexity. But a single breakthrough, a new, clever algorithm that can tame that growth curve, could suddenly solve fundamental challenges in medicine, in global logistics, in physics. The right algorithm doesn't just save time, it literally creates the future.